So we'll finish here with an application of how we can use inverses to solve systems of equations. And I'll say this isn't the only application of inverse matrices. It's not even the only one that's included in the section. There are a couple of interesting ones that are in the book. In particular, the cryptography one is kind of fun, but because we're already on a tight schedule, I decided not to include it in our main stuff. Although it is in the PowerPoint, so I'd encourage you guys to take a quick look at it, because like I said, it is kind of cool. It's this kind of thing I might toss onto an extra credit problem later in the semester. But anyway, thinking about systems, if we have a linear system, something like this, we can actually take that and instead think of it in terms of matrices, where we can think about it in terms of taking our coefficients, multiplying it by a single column matrix of our variables, and having it be equal to another single column of our constants on the other side. It's kind of a nice, clean picture that we have there for that relationship to sort of tie things off a bit from where we started with augmented matrices. You can actually think about it in terms of multiplication instead. But the reason why this is interesting to us is if we take our pieces here and we think of our matrix of coefficients with the name A, we give our matrix of variables, it's not a very complicated matrix, but it is still one, the name X, and the matrix of constants B, we can apply some algebra here to find those values X without having to do any sort of elimination, or the type of algebra that you did in high school. What we're going to do is multiply the inverse on the left. It's very important that we do this on the left, because if we multiply A inverse times A times X, that's going to be equal to A inverse times B. And if we did A inverse on the right, you get A inverse times X, that might not be anything, and you get B times A inverse, that might not be anything. It's very important you go in this order, because in this order, A inverse times A is just the identity. Well, that's just A inverse times B. But the identity does nothing to X. So we just get X is equal to A inverse times B. So, if we ever need to find the solution to a system, and we have the inverse, we can just multiply the inverse times the constants and get our values. So for example, if we want to solve the system that we have here using inverses, that is, we want to solve 3x plus 2z equals 2, 2x plus z equals -1, and 2x plus y plus z equals 5, what we can do is take that system and convert it into a system like that, of coefficients times variables equaling constants. And notice that our system of coefficients is just A from the last example. So we happen to have a nice inverse for it already. We happen to know that A inverse is -1, 2, 0, 0, -1, 1, 2, -3, 0. So if we want to find X, we just take X equals A inverse times B, -1, 2, 0, 0, -1, 1, 2, -3, 0, times the 3 by 1 system, 2, -1, 5, and we get the 3-row, 1-column solution for X, -4, 6, 7. So, we get the solution. X equals -4, Y equals 6, and Z equals 7. And you can actually verify this for yourself fairly quickly. You could see that if you took into that first equation, -4 times 3 plus 2 times 7, you'd get negative 12 plus 14, or 2. In the second one, you would have negative 4 times 2, so negative 8 plus 7 equals negative 1. And then in the third case, you would have negative 4 times 2 plus 6 plus 7 would give you 5. So this does work here. And that's all we're going to see for this stuff. For our last section of the chapter in 8.5, we're going to look at a different construction for telling some important information about matrices like these that have inverses, as well as ones that don't, in terms of a thing called the determinant. But that's for later. I'll see you when we get there.